So in this particular lecture, we are going to study a hard graph interview question that's commonly known as the alien dictionary question. So the whole idea behind this problem is that we have some sort of new alien language. And for convenience, which makes it easier to program, it uses the Latin alphabet, so anything from A through Z. However, the order among the letterings are unknown to you. So it's not going to be the normal 0 through 26 or ASCII values. But we are given a list of words. Now here's the interesting thing about this alien language. The words are sorted lexigraphically, which means that whatever we receive is the order in their alphabet. So for example, W would come before R in the alphabet, comes before T in the alphabet. This would be like if we had A, C, and F. This would be in the English alphabet, would be in the lexicographical order. So based on this, we know the orderings, and in this particular sample, we are given a correct solution. So the question is, how do we derive the orderings of the letter in this language? So in order to do this, first we just want to draw it out and see if we can come up with an actual ordering and see if we can take what we've drawn out and translate that to a known data structure. So we have W, R, and T, but then the second letter is W, R, and F. So with this word, we see that there is a redundancy. And all we really need to do is just have an edge go from R to F. So in this case, we don't know enough information based on the words to make a decision between T and F. So a crucial aspect about the input to the problem is that we must have a known solution that would break this tie. So from here, we get another word, ER, and we see ER is down here. And just like before, we see that there is a redundancy. So we would just want to create an edge between E and R, like so. And we're starting to see that the potential data structure that we would want to use is some sort of graph, which then brings into all kinds of different things that we can use. We've learned depth first search, we've learned breadth first search, we have learned topological sort, we've learned minimum spanning trees, so we did that with Prim's algorithm, we've learned Dijkstra's algorithm, and in the previous lecture, we learned about disjoint sets and union find. So now we have several tools at our disposal in order to be able to potentially solve a problem like this. Well, let's continue on this example and draw out our solution. So the next word is ETT. Well, there's two things that we can do here. One, we could just put an edge between E and T. Or what we can do is we can use that connected method that we wrote in lecture 22 to find if there's a valid path between E and T. So here we could find it this way. And we did that using our modified depth first search. So in lecture 21, we did depth first search that would print out E, R, and then T. And then in lecture 22, as we wrote a method connected, which took out one of the data structures that we use to keep track of the parents and just printed out a bool whether or not these two are connected. And we use that to determine whether or not we had a disjoint set. But this is also beneficial because we can determine whether or not E and T already have some sort of connection. And this is beneficial for precisely the scenario we're seeing here. In this ordering, we know that E comes before R, comes before T in the alphabet. But in this case, we are getting a word E, T, and T. What we don't want to happen is we don't want to have our solution unintentionally believe that E and T are connected. But for the time being, let's just put in the edge so we can analyze some potential solutions. The next one is RFTT. And so we had R and T already, but now F and T, which is here in the word, now we're putting in an edge because we now have made that decision that F comes before T in the alien alphabet. So we've made all the decisions except we don't have some sort of ordering between W and E. So we are going to see that E and R, WER, like so, has this set of connections. So if we were to come up with this particular graph, this would be our adjacency list representation. So our first approach would be, let's see if we can apply some of these things that we've learned in the past and see if this gives us a correct solution. So let's first try a topological sort. So with a topological sort, we're basically doing a depth first search, but we're just going to keep going until we have evaluated all the possible ways to get to every node. And that will get us the minimum number of edges to get to these locations. Now here, right off the bat, is going to be an example of why we can't use topological sort to solve this problem. We have R before E in the adjacency list representation, which means that the topological sort is going to go to R first. And this is problematic because the out ordering that we've determined has E and then R. But let's walk through this and see what the actual final graph would be. So first we'd evaluate R, and because we're using recursion and a stack, we would go to R and look at the first element in the adjacency list, which is going to be T. T doesn't have any output, so then we move back up on the recursive stack, and then we go from R, and we evaluate the second element, which is going to be F. When we go to F, we see that T has already been visited, so that edge between F and T is going to be removed from the adjacency list. And then when we go back up to W, we are going to evaluate the second element, which is E. Both of the outgoing edges from E are to R and T, which have already been visited. So now this would be our final topological sort. Now this does not give us a sorted result. We see that there are two potential paths. And here we have not made a decision between E and R. So topological sort doesn't work. So let's also go about this by using a minimum spanning tree. Since all the weights in this particular graph since all the edges in this graph have the same weight, basically what would end up happening is this becomes breadth first search. And again, this particular first step demonstrates why we can't use minimum spanning tree or Prim's algorithm, because we still have not made the decision between E and R. Here, what we're going to have is we're going to have W, and then it's going to put it in order of the adjacency list representation into the queue. So we're going to have R and then E. So it's going to evaluate R first. So what's going to happen is it's going to go to R, and it's going to look at T and then F. So it's going to remove W from the queue. We'll put T and then F at the end, and we're going to remove that. So now E is evaluated, and we're going to see that both of the outgoing edges from E have been visited, so they're not going to be part of the minimum spanning tree. And then we look at T. T has no output, so nothing's going to happen. And then we're going to go to F, and F's only outgoing edge goes to T, so this edge is not going to be part of the minimum spanning tree. So we're going to see that disappears as well. And just like before with the topological sort, the minimum spanning tree does not give us the exact ordering for our solution. So this is why on LeetCode, this problem is considered a hard problem, because normal algorithms that you've used, Dijkstra's algorithm for shortest path, topological sorting algorithm, Prim's algorithm for the minimum spanning tree, do not produce the solution that we need with an adjacency list representation. So we have to maintain some sort of way that we can actually know what the parent was and then replace it when we find a node closer to the result. So what do we know at each insertion, And how is this going to help us solve the problem? Well, let's consider W, R, and F. When we're initially at W, we just put in a vertex. When we get to R, we know that there is an edge between R and F. So we know the origin and the destination. And we get to T, we know that there's going to be yet another edge. And so this would be our adjacency representation after the first word. It's pretty straightforward. We know it like this. And again, when we put in RF, when we get to WR, we know that it's connected, and so we don't need to put in an edge. When we get to RF, we know that it's not connected, and we put in an edge like so. And we do ER, we know that ER is not connected, so we put in an edge like this. When we do ETT, E and T are connected, and then we make sure that we don't try to do an edge between T and T. We don't want this loop going back and forth, so therefore that will remain the same adjacency list representation. And when we get here to RF, T, and T, we know R and F are connected, and we know that F and T are here. Now this is a first example of when we can use our knowledge of previously visited results to produce a solution. So let's take a first crack at previously known results. Our previous result, we can check to see if there's an edge between R and T. If there is, we can just delete it, and now we have a subset of the solution here with R, F, and T. Likewise, we have W, E, and R. We see that there's no edge between W and E. We see that there's an edge between E and R, but then we need to check to see two back, like so. And then we check to see if that edge exists, and then we remove it, and now we have our sorted graph. So based on this knowledge, we could say that we could iterate through the elements, check to see if there's an edge between the two characters, and if not, we want to add that edge, and then we look index of origin -1 and destination. So if we have W, E, and R in that last scenario, this would be the origin, this would be the destination, and this would be origin -1. If there's an edge between these two, we would just delete it. However, we've come across another scenario. Let's consider this pair of words. We have W and T, and then W, E, R, F, and T. We put in the second word, and now if we're only looking back to, that would be R and T, and there's no edge here. So this particular approach doesn't catch this edge. So how would we actually address this? Well, it turns out that we can actually use some dynamic programming to solve this problem. And the way we use dynamic programming is we have a parent array which maintains the set of previous solutions. So let's walk through this and see what would happen. If we have W and T, we will mark all of the parents as -1, and we will put in our adjacency list representation. Now that T is in here, we're going to update the parent of T as W. So now we're going to do WRF, and now notice how R has a parent of W, and F has a parent of R. Now we're going to put in ER, and we're going to see that we have a scenario in which we now have to pick which one we're going to do. However, we don't have enough information to make a decision. We don't know the ordering of W and E. So for now, let's just leave it alone. So now I'm going to put in T as an edge there. And again, we still don't have enough information to break the tie. But now we're going to do RF, and we're going to see R and F are connected. If we do F and T, we're going to add in the edge. And now we can see what's going on here. How do we make a decision about which one we should do? Well, here's our approach. Our approach should be we have the current parent of T, which is W, and we have the proposed parent of F. So it's simple. If we say that W and F are connected in this specific order where W is the origin, that means that F should be between W and T. And so we check to see if they're connected. And now we have enough information to make a decision. And we're going to see that when I do the next animation, that what's going to change is that this is going to be updated from W to F. So now let's keep going. And now we're at WER, so there's no edge between W and E. And then we do ER, we see that there is a connection, and now E is our new proposed parent of R. So how do we do this? Well, we check to see if there's a connection between the previous parent, W, and the new parent, E. There is, so now what we're going to do is we're going to remove the edge from W to R, and then have E as the new parent of R. So this new list is beneficial because we only need to establish the parents. We don't need to actually delete all of the edges, which is beneficial in this particular example because E still has two outgoing edges. Now in this case, a depth first search would work because in the adjacency list representation for E, R comes before T because ER came before ET. But if I switched these, it wouldn't work. However, by keeping track of the parents would have updated correctly to ensure that E would have the right parent. And we're going to show several tests to prove this works. And so what we're going to do is we're going to use this, just like we used the Sentinel earlier in the semester with breadth first search and depth first search, to develop a new graph that has the precise ordering. W has -1, so it is going to not have any parent. R's parent is going to be E, T's parent is going to be F, E's parent is going to be W, and F's parent is going to be R. And we see that it works fine. So let's take a look at how we would do this in code. So in the class, we have learned about standard pair. And standard pair can keep track of both the data and the location, so data versus structure. So the standard pair, if we're correlating this, first, in a dynamic array, we'd have element 0 contains the character W with a parent of -1. The first element contains a character of R with a parent of 3. 2 contains the character T with a parent of 4. 3 contains E with a parent of 0. And 4 contains F with a parent of 1. And so this we can use to actually create our graph. Based on this information, we know W is going to be 0, and it has no parent. We're now going to create R is going to be the first one. This will be vertex 1, and it has a parent of 3. T is going to have the second element. E will be the third element, third vertex, excuse me, and F will be the fourth vertex. So now let's revisit the second. W does not have any incoming edges. R has an incoming edge from 3, like so. So we know from 3 to 1 is an edge. T has an incoming edge from 4. So we know that this is an edge, 4 to 2. E has an incoming edge from 0. So we know that, let me pick a different color here. That's our new incoming edge. And then F, 4, has an incoming edge from 1. And now if we follow it, I'll pick a final different color, pick gray. We start at W, and then we say to E, so it's going to be W. Oh, that's not the best color. I'll pick a different one. I'll pick dark blue. So we start at W, and we move to E. So that's W and E. And then E goes to R, R goes to F, and then F goes to T, like so. And that is the correct answer. And so now actually, turns out I have the animation, so let's do this again. And then we can say W, E, E goes to R goes to F, and F goes to T. So now let me show you some of the modifications I've made to a graph in order to actually make this work. First, I created a method in graph contains vertex data. And it brings in a data inside of the vertex. So let's say I would have this as W. So what I do is I go through each vertex in the adjacency list, and then I call the previously written method get vertex value. And the vertex value would be W. So I'm comparing vertex value and data. If it's true, then what I'm going to do is I will return true. Now, if I go through all the vertices, I return false. So it's basically just saying, is there a vertex that contains this data? The next approach is to write a method that returns the location of that data. So it's the exact same code, except what I'm doing is I'm returning the location in the adjacency list. I do want to note that I'm casting it to an int. And the reason I'm doing this is because I want to return -1 in the event that this vertex is not in the graph. The next method I've included in the graph is called does edge exist? And so I have an origin and a destination. And first I have the if statement, if origin is less than vertices size and destin is less than vertices size. That means that the value has to be 0 through vertices size -1. And if that fails, we automatically return false. So now what I do is I go through each vertex and I pick the origin, go to that specific vertex for the origin, and then I go through each edge. So I get the num edges that we've written before. And then what I do is I get the edge at that specific location. So iter corresponds to the number of edges. So if there's 3 edges, it would be 0, 1, and 2. And then each edge structure has a destination of the edge. So if the destination of the edge matches the destin that we're reading in, then I return true. So I check each edge in that vertex. So now I want to go into this alien.cpp function program that I've written to test. So here I have a dynamic array with a string of words. You see that again, I've done pound define, like so. Once I push those all in there, what I do is I just print them all out to the user. Next, what I do is I create the initial graph. The initial graph is going to be reading in the strings, and we're going to create this based on what we understand and how to solve the problem. Now, based on this, I want to create a parent. Now, remember, for parent, I want to use a standard pair, and the pair corresponds to the character and the int that I'm going to have its parent be. And again, remember that I picked int because I want to have this location where we get the vertex, but it could potentially have -1 in the event that that location doesn't exist, which is why I've chosen int instead of unsigned int. So now what we do is I have this for loop. And so what I like to do is I like to go over to the actual code because the for loop goes through several slides here. But the slides are there so that way you can review them as well. So here's where the for loop begins. In the for loop, I go through each word. And then inside, for jitter, I go through each character. So I go to the specific string, and then I get the total number of characters. The first thing I do is I check to see if the graph does not contain a vertex with that character. So how this piece of code works is I go to the word and then .@jitter, since it's a string, means that I'm getting the specific character. And then I'm calling that contains vertex data method that I just presented. And remember, it's a Boolean. So it's checking to see if the character is a member of one of the vertices. And if it's false, the first thing I'm going to do is I'm going to add it to the graph using add vertex. And then likewise, what I'm going to do on the parents is I'm going to push back that character. So let's say it's W. And then the second part of the pair is -1. So at this point, the first thing I've done is in the event that I'm adding a new character, we haven't established what its parent is yet. So now let's go down to the first of the two if statements. So that's here in the slide. If you want to go through this, that has all the descriptions of what I'm about to talk about as well. So this is the condition where there's at least 2 characters. If there are at least 2 characters, now we can start seeing if we want to put edges between them. So first I get the origin. And remember, I have that method that I just presented, find data index. And so I get the character that's one behind. So for here, we're at WR. And jitter is going to be here. And jitter -1 would be W. So words iter at jitter -1 is actually getting W. And it gets the location in the graph, so specifically the index for origin. And then jitter would be R, get the index of the vertex, and make that the destin. So for now, the first thing I do is I check to make sure they're not pointing at the same location. So that way, if you have that scenario where we had the word E, T, and T, we want to make sure that they're not pointing to the same place. Likewise, if alien language connected, origin and destination, this is where I check to make sure that they're not connected. So if we have W, R, and F, but then we do R and F later, before I would even try to do, if I do WF later, the first thing I would do is try to see if they're connected. And that would say it is connected because we have the edges from R of W, R to F. So it wouldn't pass. But if I had WG, this would allow me through since they aren't connected. So what we would do is we would then add an edge, origin and destination, and then I set 1 as the weight, so that way all of the edges in this particular graph have the same weight. The next thing I do here in this if statement is if the previous parent is equal to -1, meaning it didn't have a parent before, now I'm going to set that parent equal to the origin. So remember that .second is a keyword for standard pair. So .first is going to be the character, and then this .second is going to be its parent. So we initialize that as -1, but now we're updating that to origin. And now we have an updated edge. The last if statement is going to be, and for the record, it's also here on this slide, so you can review it on your own. This is the case where jitter is greater than 1, which means we have at least 3, because it would be jitter is equal to 0, jitter is equal to 1, and now we're at 2 or greater. That's why we say here, meaning there are at least 3 characters. And furthermore, I check to make sure that the previous 2 characters are not the same. So now what I do is I say, well, what's going to be my destination? Well, I look up the character at jitter, which in case would be F, and I get that destination. And then I look up the previous destination's origin. So let's say I had WF and then WE and F. What would happen is I would have W, F, and then E, and then I'd have an edge between W and F, and then an edge between W and E. But since I've gone to E and F, I now have an edge going from F to E. So what I need to do is check to see what the parent should be. In this case, what's going to happen is it's going to see that there's a path from W to E, and therefore WF should be removed, and that E should be the new parent of F. So let's see how this actually works in code. First, we say if origin is not equal to -1, so we want to make sure that we're not unintentionally removing we should only be checking if a previous parent is there, and this is there to prevent a segfault. If the origin does equal -1, then we may run into some problems. So the first thing we do is we're going to remove the old edge, and then we're going to say updated origin, and we're going to use words at iter at jitter -1. So if we have W, E, and F, that's going to give me the index of the vertex in the graph containing E. And now what it's going to do is to say parent's destined second is equal to that updated origin. So now we have fixed this particular problem. So that was the last if statement of the for loop. So what I'm going to show you next is the steps that show how I'm printing out the final results. So the first thing I'm going to do is going to print out the remaining original graph. And remember that the original graph does not have to have the final solution, and that's okay. What I'm going to print next are the parent values. So let me show you this actual code. So here I say remaining original graph, and I print out alien language. And if remember, I have a overloaded operator in graph that prints the vertex, the value, and all of the outgoing edges. What I do next is I print the parent array values. And so what I do is I go through the size of the parent dynamic array. And since it's a standard pair, I print out first, which will print out the character, and then second, which will print out the parent. The next thing I do is I put the solution, I create a graph solution. And again, all this information is on the slide, so you can review it later if you like. In this particular code, in this graph solution, I first go through each parent and I create a vertex. And I create the vertex with the data using parents iter.first. Remember, this was the standard pair. And standard pair first we defined as the character. So this will actually give us those specific graphs. And then finally, what we do is we use the second in order to be able to write the edges. So remember that the parent dynamic array, the dot second element is the origin of the edge. So if we had W, E, and then F, what would happen is F would contain 1, 0, and this would be -1, because the parent from E to F should be this, from node value 1, right? And then E's parent is 0, so we get that edge, and then W's parent is -1 because it should not have a parent. So when we go through and add these edges, this will allow us to be able to create a new graph that has the exact lexicographical ordering. So we go through each parent, and if the parent's second does not equal -1, this means that if the parent second does have a parent, then we add the edge to solution. And here's the order. First, I cast second to an unsigned int, and I make that as the origin of the edge. Its parent is iter. And then I set 1 to make all the edges equal. And then finally, I use the overloaded operator in graph to print out the solution graph. So the remaining slides contain the output of what I'm going to run and show you. So our alien.cpp is going to print out the words, the original remaining graph, the parent array values, and then we're going to see the solution graph. So let me run clear, make clean, and I'm going to run make alien. And we see that we have the original graph, and we have the several outgoing edges from E. The words were WT, WRF, ER, ETT, EFTT, and WER. So for parent array values, what we're going to see is W, T, R, F, and E. If we actually go in the order that we encounter them, we see that we go WT, and we see WRF, ETT, and so we have it in the exact order that we see them. And so with this particular ordering, the location of the dynamic array is 0, 1, 2, 3, and 4. And now based on this parent array value, we can now see what this should be. So this is the parent, so we see that F from 3 to 1 is one of the edges. From R, its parent is 4, so we are now going to put this here. And then we go to F, and its parent is 2. And then we look at E, and its parent is 0. And now we can actually trace out what the solution should be. It should be W to E to R to F to T. And so we have the correct solution represented in the parents. So now let's compare it with the actual solution graph. The solution graph has 0 as W, 1 as T, 2 as R, 3 as F, and 4 as E. And so now we can go through this and see what the actual solutions are. W has an edge outgoing to vertex 4, which is E. T does not have any outgoing edges, and that's what we want because that should be the last character. R has an outgoing edge to E. F at vertex 3 has an outgoing edge to 1. And then 4 at E has an outgoing edge to 2. And so now we have produced the exact ordering. Again, we see that W goes to E, goes to R, goes to F, goes to T. And so now we have a graph with the exact solution. So for a second test, what I've done is I've taken the exact same characters, but now I've put them in a completely different order. The order will just change the ordering in the parents array and in the graph itself in terms of which vertices contain which characters. What's going to happen is the edges will still point to the right locations. So let's run alien 2 and see what happens. You see we have a different graph, and now we have our parent values. So we're going to have 0 is E, we'll put 3 down here. 1 is F, and we'll put 4 down here. 2 is T, and we'll put 1 down here. We'll say 3 is W, and we'll put -1 down here. So we see that already we have correctly determined that W should be the first value, and then 4 is going to be R, and we'll put 0 down here. So now we are putting it backwards, right? Remember, these are the parents. So E has a parent of 3. So we see that comes from W. F has a parent of 4. We see that comes from R. T has a parent of 1. W does not have a parent. And then R has a parent of 0. And if we go through with a different color, so let me do yellow, that means that W, E, R, F, and T. So we have the correct solution. So now let's go to the solution graph. That's now using the graph data structure. So in this, again, we put these in based on the order that we encounter the character. So it should be E, F, and T. Then W, we have already encountered E, so we put in R. So we see that E, F, T, W, R, again, has the same ordering that we've encountered them in, but then the edges will give us the lexicographical ordering. So again, we have E is 0, F is 1, T is 2, W is 3, and R is 4. So now these edges represent the outgoing edges. These values represent the outgoing edges. So 0 has an outgoing edge to 4. 1, which is F, contains an outgoing edge to 2. T does not have an outgoing edge, so we see that this has worked again because T should be the last letter. W at vertex 3 contains an outgoing edge to 0, and then 4 contains an outgoing edge to 1. And so now let's go through again with yellow here. We would see that W goes to E, E goes to R, R goes to F, and F goes to T. So again, we have received the correct answer, W, E, R, F, and T. So for alien 3, I have come up with an interesting case, and this is going to be this is going to be the last case that we're going to test in this video. So first I have W and T, and then I have a very long word, and W is at the beginning and T is at the end. So what's going to happen is all of these edges are going to be in that specific order. We need to make sure that the W and T edge is no longer there and T's parent becomes I instead of W. So let's run alien 3 and see what happens. Putting into the same algorithm, we say we have the remaining original graph, and we see that W needs to skip over from 2 here, and I needs to go back to 1. I'm sorry, my apologies. I's parent is 1, right? And then here, E has the outgoing edge to 2, like so. If we go to parents, we're going to see that again, W is at the beginning, T has a parent of 9. E has a parent of 0. R has a parent of 2. So I'll put 0, 1, 2, 3. F has a parent of 3. G has a parent of 4. H has a parent of 5. A, and then I, let's say B, and then I is 8, like so. So 9, the difference is here, 0, right? This does not, this is -1, excuse me. So W does not have a parent. E's parent is 0, like so. And then the rest of them we see go like this. But T's parent is 9. See that 9 is I. So we're going to see that this one goes here. So the actual ordering is W, E, R, F, G, H, A, B, I, and T. And if we look at this final graph, we're going to see that that's the ordering that we get. So again, we have 0, T is 1, E is 2, R is 3, F is 4, G is 5, H is 6, A is 7, B is 8, and I is 9. So this output, again, has the outgoing edges. So we'll do this. W has an outgoing edge to 2, like so. E has an outgoing edge to 3. 3 has an outgoing edge to 4. 4 has an outgoing edge to 5. 5 has an outgoing edge to 6. 6 has an outgoing edge to 7. 7 has an outgoing edge to 8. 8 has an outgoing edge to 9. And then 9 has an outgoing edge to 1. And so if we follow this ordering, it's WE, R, F, G, H, A, B, I, and T, which is what we expect our answer to be.